All right, hey guys, so we are moving forward with chapter 9, and we're going to start talking about position, velocity, and acceleration. Now, we already talked about position, velocity, and acceleration first semester, but most of the time that was because we were given position and we took derivatives to get velocity and acceleration. So now we're going to start looking at what happens when we need to use integrals. So for most, but not all, of the position, velocity, and acceleration questions you're going to get on the AP exam, you're going to be given a table, graph, or equation of the velocity function. So when we define these words here, we've already defined them in the past, but when we define them here, we're going to be talking about them in terms of velocity. Now that's not going to be the only way that they appear on the AP exam, but it's going to be, for the most part, how they appear. So the displacement of an object is the difference between where an object starts and where it stops over an interval of time. So we're going to go ahead and call that interval just from A to B. So if I want to find the displacement, all I need to do is take the integral from A to B of v of t dt. Now it's important to notice that this integral gives us the displacement. It doesn't give us the position. So we have to be careful because we know that the first derivative of position is velocity. So we would think that the integral would be the position, but we have to be careful. When we're asked to find an object's position at a given time, we have to have two pieces of information. We need to know the initial position, or the starting point, and then we also need to have the velocity function. If we don't have those two things, we can't get the position of an object. So if I'm going to write that over here, this is going to be then our initial position plus the integral from A to B of v of t dt. That is what will actually get us our position. So you'll notice that last part there, that integral, is just the displacement. So to get our position, we need to know where did we start and then how far did we move. That'll tell us where we're at. That should make sense. Okay, total distance traveled. So when we integrate a velocity function, it automatically considers the direction. We can cross off this blank here, sorry. It automatically considers the direction an object is traveling. So if an object goes backwards, it subtracts that value. When we integrate. So that means then for the total distance traveled, since we want to consider all of the distance as positives, it's going to change what we're doing. So I just really screwed that up. Okay, so for total distance traveled, we want to consider all distance traveled as positive, even when we're going backwards, which means when we look at the integral, it's still going to be from A to B, but now we want the absolute value of the velocity. Because it doesn't matter if I'm moving backwards, that's still part of the distance that I've traveled. So when we take the absolute value of it, it'll give us the total distance as opposed to just the displacement. Okay, and then speed increasing versus speed decreasing. So to determine whether an object's speed is increasing or decreasing, we need to compare the two values for the velocity and the acceleration. So we need to look at both pieces to decide whether the object is speeding up or slowing down. All right, so if the velocity and acceleration have the same sign, then we know that the object is speeding up. Or that the speed is increasing. All right, but if the velocity and acceleration at that point have different signs, then that means the object is slowing down, or the speed is decreasing. And we've talked about that before as well. So now we're just going to be looking at it in a little bit of a different context. So let's see what some of these examples are going to look like then. So question 1 says the graph given shows the velocity function for an object. Wow, that really went all over the place. Sorry about that. Moving along a straight line from t equals 0 to t equals 8. T equals 0, the position of the object is 5. So that's going to be important. There's a couple things here. The fact that this is the velocity function, the velocity graph, makes a big difference. So you want to make sure you take note of that. You also want to make sure that you take note of the fact that it gives us this initial position. All right, so at time t equals 0, the position of the object is 5. That's going to be important as we move through. So, question A says, when is the object at rest? When is it moving right? When is it moving left? And justify your answers. Well, we know that for the object to be at rest, that means that the velocity is equal to 0. So, if I want to be able to say when the object is at rest, so the object is at rest at, well, let's figure out where the velocity is equal to 0. Since this is the velocity graph, all I need is the x-intercepts, which means the velocity is 0 at t equals 5 and t equals 8. T equals 5 and t equals 8 because the velocity equals 0 at these values. All right, then we want to look at when is the object moving to the left. Well, we know that the object is moving to the left when the velocity is negative. So if it's moving to the left, we're looking for where is v of t less than or equal to 0. So the object is moving left. Moving to the left. All right, well, let's figure out where the velocity is less than or equal to 0. So that means we need anything that is below the x-axis. So from 5 to 8. So the object is moving to the left on the interval 5 to 8 because the velocity is less than or equal to 0. And I realized I kind of skipped the other one. I went in the wrong order, but it doesn't really matter. But when is the object moving to the right? So the object is moving to the right anytime the velocity is greater than or equal to 0. So the object is moving to the right. Well, velocity being greater than or equal to 0, since this is the velocity function, I want wherever it's positive, so where it's above the x-axis. So that would mean from 0 to 5. So the object is moving to the right on the interval from 0 to 5 because v of t is greater than or equal to 0. So notice for each of these I had because on my answers because it asked us to justify our answers. So it's not just what are the values or what are the intervals, you have to include that justification as well. All right, so part B says evaluate the integral from 1 to 6 of v of t dt and explain the meaning of the result. So I think the first thing we should do then is actually find the integral. So if I want to do the integral from 1 to 6 of v of t dt, that means I just need to find the area under the curve. Now be careful because we're starting at 1. So we're going to start here and we're going to go all the way through 6. So I'm thinking the best way that we can do this is it looks like if we go to 3, we can have a trapezoid there. So let's see, the height of our trapezoid would be 2, so 2 over 2. Base 1 would be 1 and base 2 would be 2, so 1 plus 2. So that gets me from 1 to 3. And then from 3 to 5 I have a triangle with a height of 2 and a base of 2. So 1/2 2 times 2. And then this last piece from 5 to 6 is below the x-axis, so it's negative. And it's a triangle with a base of 1 and a height of 2. And so let's see, we get 3, this gives me 2, and then that gives me 1. So 3 plus 2 plus 1, that means the integral ends up being 4. So the value of the integral is 4, and now we need to actually explain the meaning of the result. So if we think back to what it means when we do an integral of velocity, we know that the integral of velocity is actually displacement. So we need to say then the displacement of the object is 4, and then we need to include the time interval. So we went from 1 to 6. So the displacement of the object is 4 over the interval t equals 1 to t equals 6. So there's 3 really important things that we need to include there. We have to include the word displacement because we know that the integral of velocity is displacement. We want to include the value of the integral, and if there were units, we would want to put the units there with it. And then we want to include the time interval that we're talking about. Okay, for part C asks what is the position of the object at t equals 5? Well, we know that position means that we need the initial value plus the integral of velocity. Well, we were told our initial value up here. At t equals 0, the position of the object is 5. So my initial position is 5. And then the integral that I'm going to look for velocity, since at t equals 0, the position is 5, we have to start our integral at 0. And then it wants us to stop at 5, so from 0 to 5. All right, so we can use pieces of part B to help us do this, but we know that we're going to have 5 plus, let's see, the integral from, if we do 0 to 1, then that's just this square, which is 1. And then plus, we know that this part here, this 3, was the integral from 1 to 3. And then the integral from 3 to 5 was this 2 that we had there. And so we get that the position of the object at t equals 5 is 11. All right, and again, this 3 and 2 came from the work that we did up here in part B. You can do it again if you want, but I'm going to save some time there. Okay, total distance traveled. So we want to be careful here because we know that total distance traveled means we want the integral from 0 to 8 of the absolute value of the velocity function. So we want to make sure that we include all of the values there. Well, I'm going to break this up as the integral from 0 to 5 of v of t dt, because from 0 to 5, I'm above the x-axis. And then plus, I'm going to do the absolute value then of the integral from 5 to 8 of v of t dt. And the reason I did that is because from 5 to 8 is where I have a negative velocity. So if I just take the absolute value of that, I'll be good. Well, we just found the integral from 0 to 5 over here in this problem. So the integral from 0 to 5 was everything except for this 5 here, which means the integral from 0 to 5 is actually 6. All right, and then we need the absolute value of the integral from 5 to 8. Well, from 5 to 8, we can see that that's a trapezoid. So the height of the trapezoid is 2. And then base 1, I'm going to call the x-axis here, so that's going from 5 to 8, which is 3, plus this base would be 1. And so we have 6 plus 4, which means that our total distance traveled is going to be 10. Now, if we had units, we would need to be including the units in all of these, but they didn't give us any, so. All right, one more part for this question. So at time t equals 2, is the object speeding up or slowing down? Explain your answer. Well, we know to decide whether the object is speeding up or slowing down, we need the velocity at time t equals 2, and we need the acceleration at time t equals 2, because we need to compare those two values. So the velocity at time t equals 2, since this is the graph of velocity, we can just look at what's the function value at time t equals 2. So it's somewhere between 1 and 2. It doesn't really matter what number it is, but I know that the velocity at time t equals 2 is greater than 0 because it's a positive value. And then I need to think about the acceleration at time t equals 2. We know that the acceleration is really the derivative of velocity, which means I can just look at the slope at time t equals 2. So go back up to your graph, and we can see that time t equals 2, that's a positive slope, which means the acceleration at 2, regardless of what it is, it's going to be positive. So our answer then, if we're going to explain it, we know that the object is, let's see, since velocity and acceleration are the same sign, the object is speeding up. At t equals 2 because v of 2 and a of 2 are both positive. You could also say that v of 2 and a of 2 have the same sign. However you want to word that is fine. Okay, moving on. We've got one more example, and you're going to need your calculator for this because this is a calculator question. So if you don't have your calculator, you're going to want to grab it. So a particle moves along the x-axis. They give us the velocity function here. At time t equals 0, the position of the particle is x equals 1. So that's our initial position there. So part A says find the acceleration of the particle at time t equals 2. Is the speed of the particle increasing at 2? Why or why not? Well, if we're looking for the acceleration at time t equals 2, we know that that's really the first derivative of velocity at time t equals 2. So since this is a calculator question, I'm going to use my calculator to do that. So if I want to take a derivative, I know that that's math 8. And I'm going to go ahead and plug in my function then. So negative x plus 1 sine of x squared over 2. And I'm going to take the derivative at x equals 2. And so I get that that is not the right answer because this is in degree mode. All right, that was good. Glad I checked that. So make sure you are in radian mode. My bad about that. There we go. Okay, so we know that the acceleration at time t equals 2 is going to be 1.588. And again, if we had units, we would include them, but we don't. So There's that. Okay, is the speed of the particle increasing at time t equals 2? Well, for the speed to be increasing, we need to look at the acceleration and the velocity at time t equals 2. So we already know that the acceleration at time t equals 2 is 1.588, which is a positive number. So now we need to figure out what is the velocity at time t equals 2. Well, that means then just substitute 2 into this function. So negative 2 plus 1 times the sine. 2 squared is 4, divided by 2 is 2, so I'm just going to do the sine of 2. And we get that the velocity is negative 2.728, which we know is less than 0. So when we look at this, the acceleration is positive, but the velocity is negative, which means that the speed of the particle is not increasing at this point. So the speed of the particle is not increasing at time t equals 2 because a of 2 and v of 2 have different signs. All right, for part B, it says find all the times t in the open interval from 0 to 3 when the particle changes direction. Justify your answer. So if I'm looking for when the particle changes direction, it means that I'm looking for when the velocity changes sign. Because we know that if the velocity is positive, we're moving to the right. If the velocity is negative, we're moving to the left. So we're looking for where the velocity changes sign, which really means we're looking for x-intercepts, because that's when the velocity is equal to 0, and then we want to see if it crosses the x-axis. So we're going to go ahead and grab our calculators, and we're going to plug this function in. So negative x plus 1 sine of x squared over 2, and I'm going to change my window to just be from 0 to 3 because that's the interval that I'm looking for. And let's see what happens. Okay, there we go. So that's good. We can see that not only does it have an x-intercept right here, but that it crosses the x-axis. So we just need to find that point. So we're going to calculate the 0. And let's see if I want my left bound. I'm here, and then my right bound. I'm going to go here and tell it to guess. So I get that my 0 is at 2.507. So t equals 2.507. So again, we did where the velocity is equal to 0 and changes sign. I know we wrote it over there, but just to help us out here. So at time t equals 5.07, the particle changes direction. At t equals 2.507 because velocity changes from negative to positive at this value. All right, because we went from below the x-axis to above the x-axis. Find the total distance traveled by the particle from time t equals 0 to time t equals 3. So what we are going to be doing is we are finding the integral from 0 to 3 of the absolute value of v of t dt. So this is just a straight up calculator question, which is really kind of nice, and there's no justifying this one. So since I want an integral, I'm going to do math 9. I'm going to go from 0 to 3. And now I need to put the absolute value in there. So I'm going to go back to math, and I'm going to go over to number, and the first one there is absolute value. And then I'm going to plug in my function. So negative x plus 1 sine of x squared divided by 2. And then let's see, dx, and hit enter. And it's thinking. Okay, there we go. So we get that the total distance traveled is 4.334. And there we go. That's the total distance traveled. We don't have to justify anything, so that's kind of nice. All right. During the time from 0 to 3, what is the greatest distance between the particle and the origin? Show the work that leads to your answer. So if it's asking for the greatest distance between the particle and the origin, that's really just a fancy way of saying what is the absolute max or min. All right, and really we're going to pick the one that's the furthest from 0. So whichever is furthest from 0, because we want the distance to be the greatest from the particle to the origin. So we know that in order to find an absolute max or min, we need to know where the first derivative is equal to 0. So the first part is figure out where is v of t equal to 0, because those are our critical values. Well, we already found that in part B. So at time t equals 2.507, we know that the velocity is equal to 0. Then the second thing we need to do is we need to make our options chart. All right, and we know then that in our options chart, we are going to have to include the endpoints and the critical values. So our endpoints are 0 and 3, and the critical value that we have is 2.507. Sorry. Okay, so position, we know, is going to be the initial plus the integral. So we have to go back up to the top, and they told us that our initial position at time t equals 0 is 1. So that means then that I am going to do 1 plus the integral from 0 to 0 of v of t dt. And we know the integral from 0 to 0 is just 0. So at time t equals 0, the initial, or the position is 1. Then I'm going to take my initial position, which is 1, and I'm going to do the integral from 0 to 2.507 of v of t dt. And I'm just going to put that in my calculator. So 1 plus math 9. I'm going to go from 0 to 2.507 negative x plus 1 sine of x squared over 2. And I get negative 2.265. Okay, and then for time t equals 3, I'm going to do 1 plus the integral from 0 to 3 of v of t dt. I should have moved my 3 down a little bit, but I think you guys get the picture. So we're going to do this same integral. I'm just going to actually go up here then, and I'm going to change, so I don't have to retype the whole thing. I'm just going to change this bound to be 3. So I get negative 1.197. Okay, now I have to actually answer the question though. So it's asking what is the greatest distance between the particle and the origin, and then justify our answer. So we're going to say then, I'm going to go over here where I've got some room, t equals 2.507 is when the particle is furthest from the origin. And the nice thing about the AP exam is that this options chart shows the work for you. That is your justification. And then the second part also asks, it says, what is the greatest distance? Sorry. So the greatest distance is negative 2.265. Okay, because that's clearly the farthest from the origin when we look at those three values. I know this video got a little long, I'm so sorry, but this is important stuff. These are exact AP questions from before, so hopefully you found it valuable. We will do some practice in class. Bye!